Hello and welcome to my talk on performance analysis of matrix-free conjugate gradient kernels using SYCL. My name is Igor Barata and I'm a postdoc at the University of Cambridge. I'm part of Professor Garfwell's group, and this work was also done in collaboration with Chris Richardson. This talk was motivated by our need to understand the performance of finite element solvers on different architectures, but for that we had to take a few steps back and look closely at some basic kernels, which are part of many numerical methods in science and engineering. I will start with some motivation, why SYCL, and why do we care about heterogeneous computing. Then I'll talk about some simple kernels and the performance model we use. Finally, we'll show some experimental results and how to use this simple model to really understand the performance of the kernels from the strong scale limit, we are talking about hundreds of elements, to the performance saturated limit, millions of elements. But first, why should we care so much about heterogeneous computing? This is motivated by trends we see in supercomputers. Not only CPUs have got lots and lots of cores, but also we can note an increasing number of architectures composed of CPUs and accelerators. This trend can be driven, for example, by the need to reduce power consumption. So we are talking about energy efficient architectures. Here we can see the top 500 supercomputers from the latest top 500 list. 3 out of 5 supercomputers use an NVIDIA GPU plus a CPU from different vendors, but also 17 of the 20 most energy efficient systems use GPUs. The SYCL landscape is even more diverse. We'll probably have a combination of many core CPUs with dedicated accelerators, GPUs in most cases from different vendors. For example, Intel, AMD, and NVIDIA. And possibly with different software stacks and different programming models. And this poses a real challenge for computational scientists. We believe that SYCL could be a way to tackle this issue, since with the same code we can target multiple architectures. Since our code base already uses modern C++, we decided to investigate the use of SYCL as a parallel programming model. It has some appealing features. For example, it uses completely standard C++, so no pragma, no new language, and it's an open standard that's likely to influence the future of C++. There are multiple implementations available, but for the results we're going to show today, we used only HipSYCL and Intel SYCL from the LLVM fork. And as things are moving so fast, we highlight the tags of the versions that we use to produce the results that we're going to show later. So before looking at the actual kernels that we are going to work with, I just want to give a brief summary of the finite element method, especially because we are looking at matrix-free solvers, which are more intertwined with the discretization. The idea of the finite element method is that you can divide a big computational domain into small units of work, and these small units of work can be processed in parallel. Even though the kernels we are going to investigate here are standalone and not necessarily part of a finite element code, our end goal is to develop some portable matrix-free solvers with Phoenix to solve real-world engineering problems. For example, we are working with simulation of new electric propulsion systems. I hope this small video on the right is able to highlight some features of the finite element method. In its standard approach, the PDE that encapsulates the physics is represented as a sparse matrix. So one of the main computational kernels is the computation of this sparse matrix. And we perform this operation by first computing a local dense matrix, which can range from 3 by 3 to 1000 by 1000 for each element in the mesh. And then we add this local matrix to the global sparse matrix by using some kind of local to global map. And once we have this matrix, we can interface with a wide range of linear algebra backends to solve the underlying system of equations ax equals to b. An alternative is to use the action of A, since some iterative methods only use the matrix A to compute the matrix vector, we can compute the action of A to a vector using the local operator without assembling the full matrix or even the local matrix. This is really important for this class of memory-bound problems because we reduce the amount of data to stream from and to main memory. One of the most popular methods to solve the system of equations AXB that we mentioned before is the conjugate gradient method. In its simplest form, it can be described by this simple pseudocode on the left. It can be implemented using just a few unique kernels, the matrix vector product, line 5, 2 inner products, lines 6 and 9, and 3 vector updates, lines 7, 8, and 10. Since the inner products and vector updates can be found in many BLAS libraries, we are going to focus on their performance as we have a baseline to compare to. The third kernel we are going to investigate is the fused update. In a single kernel, we can compute 2 vector updates and 1 dot product. As we're going to see later, all these kernels are memory bound, and our performance metric is then the observed memory bandwidth. Our first kernel is the vector update using an ND range kernel. Here n is the size of the array and WGS is the size of the work group, or how many work items per work group. For a vector of size n, this kernel requires 2 n reads and n writes, and 2 n multiplications and n additions. So we can compute the arithmetic intensity for a double precision vector as 3n over 24n, or simply 0.125. The second kernel is the inner product using the SYCL built-in reductions. Compared to the previous kernel, we have here an extra parameter, BS, which is the number of elements that each work item will be individually responsible for reducing. We highlight the declaration of the reduction in the code, which from the user's point of view is something really straightforward. The use of these built-in reductions is really promising, since in theory the best implementation for a given architecture could be selected at runtime. In practice, however, this is still a work in progress, and some implementations use global atomics to compute the reduction. A simple implementation, which is not really investigated in the paper but has the potential to reduce latency, is the use of group algorithms. Each work item first computes a local reduction, and then the group cooperates to consolidate this reduction. And finally, the leader of each group can update the global sum using global atomics, but in this case we reduce the number of times we call this atomic reduction. The final kernel that we are going to look is a combination of two vector updates and 1 inner product. These 3 operations can be combined, fused into a single kernel. This can reduce memory movement, and by increasing the amount of work in a kernel, the impact of latency can possibly be reduced. Without fusion, for example, the same operation would require 5n reads instead of 4n. And the implementation is self-explanatory. We simply add the vector updates to the inner product kernel. So, to model these kernels that we know that they are memory bound, use a simple linear equation. The time to execute the kernel can be decomposed into 2 parts, one fixed and one variable part. And this time can be measured experimentally. NB is the number of bytes accessed. For example, given the size of the vector, we can compute this quantity as we did in the previous slides. The values T0 and WA, highlighted in the slide, can be estimated by applying a linear regression to the measured data. So we have NB as input and T, and then we can compute T0 and WA. Ideally, WA should match the specification of the vendor and T0 should be as small as possible. Of course, there are some physical limitations to T0, but it can also be affected by the implementation, as we're going to see later. Finally, we also have W, which is the observed memory bandwidth, and it's just the ratio of bytes accessed by the execution time. However, this model has an important limitation. It ignores multi-level memory caches, but it's a good approximation for our kernels because each entry of the vector is only accessed once. Now we are going to show a few numerical experiments and how to use the performance model to get an understanding of the performance of the kernels we talked about. These two graphs now shows the observed memory bandwidth for the vector update kernel on the A100 GPU. On the y-axis we have the array length, and on the y-axis we have the observed memory bandwidth. Solid lines are for experimental data, and dotted lines are for the fitted performance model, and we can see that they match really well. For large enough workgroup sizes, the measured asymptotic memory bandwidth is very close for the two SYCL implementations and CoBLAS. CoBLAS can be seen here in black. And for small arrays, the observed memory bandwidth is really low, which characterizes a latency bound region. This latency bound region seems to be more severe for SYCL. This table presents the performance models from the previous graph on the A100 GPU, and the parameters that we get here are latency and asymptotic memory bandwidth. As expected, the estimated asymptotic memory bandwidth for both implementations are very close to the one measured for CoBLAS, except for workgroup size of 32, where both implementations get only 50% of the theoretical occupancy. Increasing the workgroup size to 64 makes it possible to achieve full occupancy. However, the latency for SYCL is 2 to 3 times higher when compared to CoBLAS and Intel SYCL. For the Intel SYCL implementation, latency is no more than 10 microseconds. It's important to note here that both implementations, they use the same backend, so the difference in latency could be explained, for example, by how they interface with the backend. This table now presents the same results, but on the Ice Lake CPU node. The fitted performance models parameters are again latency and asymptotic memory bandwidth. However, the results are reversed. In this case, the latency is higher for Intel implementation compared to SYCL. For both implementations, the asymptotic memory bandwidth is quite similar, and it's also similar to the one obtained by the string benchmark. As expected for CPUs, WA is agnostic to the workgroup size. However, contrary to the previous case, the implementations use different backends, so SYCL uses OpenMP and Intel SYCL uses OpenCL backend. So, we now consider the inner product kernel. We show the measured observed memory bandwidth on the A100 for batch size 16 and for different workgroup sizes. The performance of the built-in reduction is reasonable for SYCL compared to CoBLAS, but is poor for the Intel implementation using CUDA backend. At best, the Intel implementation reaches less than 30% of the CoBLAS asymptotic memory bandwidth. But we need to note here that in this graph, Intel SYCL implementation is using compare and swap atomic instructions, but even with native atomics, it wasn't able to achieve the same peak performance as SYCL or CoBLAS. A possible explanation for that is the use of global atomics to compute the reduction without any group cooperation. In other words, in the implementation, each work item seems to be updating the global sum directly. So this table shows the fitted parameters from the last slide, and we can observe a high latency for Intel SYCL compared to SYCL and CoBLAS. The SYCL latency is closer to CoBLAS for this case, but it is still high. For the Intel SYCL implementation, the latency is more than 10 times higher than for CoBLAS. In this particular case, each work item is responsible for reducing 16 elements of the array. But maybe we can improve that performance if we give more work to each work item. As we mentioned before, the Intel SYCL implementation is not using native atomics, which can explain part of the poor performance. So, increasing the batch size, or in other words, giving more work to each work item, improves the Intel SYCL performance, but the latency is still high when compared to CoBLAS and SYCL. For this table, we use block size of 256. That means that each work item is responsible for reducing 256 elements of the array. So that means that it's possible to hide the effects of latency caused by global atomics by giving more work to each work item or to each kernel. Now we consider the fused kernel, which has the potential to better hide latency and decrease the amount of data to load from main memory. The CoBLAS implementation uses standard API calls, so they are not fused, and we don't show the reference here in these graphs. With SYCL, the performance is insensitive to the workgroup size, and for Intel SYCL, the workgroup size needs to be greater than 128 before the asymptotic memory bandwidth is achieved. We now look at the fitted parameters from the previous slides. We don't have a reference for latency because the calls to CoBLAS are not fused, but we can see that both implementations are on par in terms of asymptotic memory bandwidth. For latency, however, SYCL outperforms the Intel SYCL implementation, but it can be due to how they implement their own reductions. In other words, for large arrays, both implementations have similar performance, but for small arrays in the region dominated by latency, SYCL has a better performance. So this graph is a bit different from the others I showed before. It shows relative performance. In the x-axis, we still have the array length, but in the y-axis, we have the execution time normalized by the time to execute the same three operations using CoBLAS. For both SYCL implementations, we use workgroup size of 512. It's clear that the fused SYCL kernels are nearly always faster than the unfused SYCL kernels, and the fused SYCL implementation is faster than the fused Intel SYCL implementation. This is true for small arrays, as we predicted by looking at the latency in the previous slides. For small arrays, the CoBLAS implementation is faster than both SYCL implementations, which can be due to the lower latency. In this region dominated by latency, the fact that CoBLAS is accessing much more data is not relevant, but we can note that for large arrays, fusing the kernels with SYCL starts to pay off. We can perform now a similar analysis for both implementations on the Ice Lake CPU node. On the left-hand side, we show the observed memory bandwidth by array length, and on the right-hand side, we show the fitted model parameters for the Intel SYCL implementation. They both achieve around 300 gigabytes for asymptotic peak performance, meaning that for large arrays, their performance is pretty much similar. But we can observe some cache effects for SYCL, but not for Intel SYCL. For this graph, we run the same kernel 300 times, and we see that SYCL implementation is able to explore the CPU cache hierarchy, but since the latency is so high for the Intel implementation, the same cache effect is not observed. Which means that the latency can hide the benefits of use of fast memories. This can be seen more clearly in this relative performance graph. Again, in the x-axis we have the array length, but in the y-axis we have the execution time normalized by the time to execute the same three operations using MKL. MKL is generally faster for small arrays, and for large arrays, using the fused kernels start to pay off again. But a surprising fact is that for small arrays, if kernels are allowed to make use of the cache hierarchy, SYCL performance is considerably better, so orders of magnitude better than the Intel implementation. All in all, our results indicate that for large problems, the performance of both SYCL implementations is on par with vendor libraries for memory-bound kernels, and for small arrays they have different performance, but in general they do reach the asymptotic memory bandwidth at some point. Latency can still be a bottleneck for small arrays and can also affect strong scaling. The issue with compare and swap atomics that I mentioned before has been fixed in the LLVM fork, and I've got different results when I run the same results, the same benchmarks yesterday. It shows that things are developing quickly, and I showed just a snapshot from a few months ago. In this presentation, we look only at simple memory-bound kernels that are part of the CG method, but in general, the performance of the solver also depends on the evaluation of the matrix action and preconditioning, which is what we are looking at the moment, and I hope to be able to present these new results soon. I'd be happy to hear any suggestions of improvements, and thank you very much for your attention.